Kinetic usually meaning movement. We have V there to indicate movement. Kinetic energy is not zero if we have some mass and an object is moving. If we think about classical particles, classical physics, all objects are going to have three things. All objects have mass, they have a speed, and they have a position. Each of these lends itself to an energy. Speed is related to kinetic energy. Position is related to potential energy. And the symbol that I use for potential energy is a capital U. And the mass is associated with rest energy. I think I did leave capital I. All right. Now, kinetic energy formula is right over there. You're working on your Nobel Prize winning topic in physics, and you're trying to figure out what's the formula for kinetic energy. Well, it's 1/2 mv squared. That is the formula. If you get to that video, or if you watched it, you know this is the one formula I expect you to have memorized. If I ask, what is the formula for kinetic energy? Your response is, in unison, 1/2 mv squared. Let's give it a shot. And I am serious. Every voice. What's the formula for kinetic energy?
1/2 mv squared.
That wasn't too bad. Get it? Did you say it?
Yeah.
Okay. So throughout this course, if I ever say, what's the formula for kinetic energy, your response will always be
1/2 mv squared.
All right. 30 years from now, if I run across you in the street and we look vaguely familiar to each other and we eventually figure out we know each other from this moment, I should be able to ask you, what's the formula for kinetic energy? And your response will be 30 years from now,
1/2 mv squared.
hopefully with more enthusiasm. But yes. Now, if I ask you what's the formula for potential energy, the response is, which one? There are several formulas for potential energy. So let's talk about why there would be. All right, any questions on this before I erase it? All right, forces are broken down into one of two types. There are conservative forces, and let's see if we can get it right there. Conservative forces. And cleverly, non-conservative. So generically, I can call F sub C and F sub NC. Every force is going to be one of these two things. Now, there is a formal definition for conservative force, but I will go ahead and tell you the list of all the forces that we have done so far that are conservative. Done. That's the entire list of all that we have dealt with so far in this course that are conservative. All the rest of them, non-conservative. There are other forces that we will get in this course. Gravitational force includes weight. Weight is conservative. And then sort of ideal elastic force. An ideal slinky or an ideal rubber band. And the I disappeared. when we get to elastic forces, the symbol I will use for that is F sub S for spring. I don't use E, which would really be more convenient for elastic, but I reserve F sub E for electric force. Conservative forces change energy from one form to another. A conservative force will change potential energy into kinetic energy or kinetic energy into potential energy. Non-conservative forces transfer energy between objects. As sort of implied by all of this, conservative forces conserve energy. Non-conservative forces don't conserve energy within an object itself. Every conservative force has its own potential energy formula. I'm just going to write them up here without much justification other than just to give you a sense of what that's talking about there. So the conservative force, if we have, well, weight is an example there. So weight W equals mg. The potential energy formula associated with that is mgh plus a constant. This plus c, this is just some constant. If we're dealing with the generalized gravitational formula, the gravitational force formula, G(1) and 2 over r squared. The potential energy formula associated with that is negative. Big G, mass 1, mass 2 over r. It looks a whole lot like it except the negative sign and the r. Ideal elastic. This K right here, this is a lowercase k. This is known as the spring constant. The potential energy formula associated with that is 1/2 K delta x squared. As it turns out, I've written down one work energy formula. I said that the total work is equal to the change in kinetic energy. Well, non-conservative work causes a change in energy. So if I have a non-conservative force doing work, that's equal to the change in energy. And then, I want to touch on that at some point. So I know that energy is kinetic plus potential, kinetic energy plus potential energy. Again, rest energy is out there too, but I'll talk about that in a moment. So the change in energy is the change in kinetic plus the change in potential energy. The net work, which is the work done by the total force, is equal to the conservative work plus the non-conservative work. That's all the way choices are there. So therefore, my non-conservative work, oh, sorry, wrong one, I wanted conservative. So my conservative work is equal to the net work minus the non-conservative work, just subtracting that from both sides. And my net work is equal to the change in kinetic energy minus my total work, which is the change in energy, which is the change in kinetic plus the change in potential. And so we end up with the conservative work is equal to the negative change in potential energy. We have three work energy formulas right there. that will serve as the basis for pretty much solving all of our energy problems. Physics problems, energy problems. Physics problems about energy. Questions up to here? And again, there's videos also covering a lot of the stuff in more detail. All right, so let's hit a couple miscellaneous topics to finish it off. Rest energy, all of you know the formula, although you probably, if I said write down the formula, you probably wouldn't know it. But to start you out, E equals, there we go. The rest energy formula, the only difference is that m sub 0 c squared. It is the energy an object has just because it has mass. This m sub 0 here, this is the rest mass. And the rest mass is the mass an object has when it is at rest relative to the observer. So in lab, when you put it on the triple beam balance, the triple beam balance is there, you're there, it's at rest relative to you, you're finding the rest mass. The difference between mass and rest mass does not have any effect until we start getting into things that are traveling around 30 million meters per second. That's when we start to care. And that is not in this course. I bring it up just because if we're going to talk about energy conservation, then if I strike a match, we're going to lose mass, aren't we? And if I strike a match, capture all the ash, find the mass of the ash that came off of the match plus the mass of the burnt match, it will not add up to the mass that we originally had. That difference in mass got converted into energy, which is what we saw as the flame. Whenever physicists run into these situations where it looks like energy is not conserved, they create a new energy. The other thing is units. Oh, come on, we can do it. What's the formula for kinetic energy?
1/2 mv squared.
Not quite as zing as before, but that was nice. If we look at, if I have a 2 kilogram object cruising along at 3 meters per second, what is the kinetic energy? I'll get 1/2 times 2 kilograms times 3 meters per second squared. And mathematically, I get 9 what?
Kilograms meters per second squared.
Be careful how you word that. If you generally say kilogram meters per second squared, that's a Newton.
Is it kilogram meter squared per second squared?
There we go. Now, this is too much for physicists. They look at that and they go, oh, God, do I have to write all those letters? And so they came up with a new one. This is a joule. So the unit of energy and work is a joule. Notice also that work is force times displacement. So that is also a Newton meter. A Newton meter is equal to that, which is equal to that. These are all interchangeable at this point in the course. When we get to rotational motion, we're going to come up with something called torque, which also has units of Newton meter, but those are not joules. It's just one of the fun things with physics is the fact that I can have Newton meters that equal joules in one case and not joules in another. Work and energy, joule. Torque, not joule. And on that dynamic note, I think that you should rejoice in a different location. Possibly rejoice with a different potential energy.